Okay, for this last section, we are going to talk about variational approaches to, I can spell approach, to finding optimal operators that have good overlap onto the states of interest. So here we're going to consider that we have a basis of operators. So O1, O2, O3, etc. And what we want is to find linear combinations, just like we did for matrix prony, with optimal overlap onto a set of energy levels. And remember that we're talking about using Lusher to find scattering information, and the key to being able to use Lusher is to have a reliable set of energy levels. And we can't really rely on just being able to extract the ground state, because then we would have to have a different volume every time we wanted to calculate another energy level, and that is just too expensive. So we have the lattices that we have. We would like to extract as much information as we can out of them without having to recalculate new lattices. So, okay, so the thing we're looking for is some linear combination so we want to find the set of weights VI such that this linear combination given by omega has optimal overlap onto some state n. Okay, so writing down what I just said, I want to think about this as a variational principle. So I want to maximize or minimize something. So what is that I want to do? So I want my operator, my linear combination of operators, when acting on the vacuum, to give me the eigenstate n that I'm interested in, plus some extra bit. So let's say the set m for m not equal to n are all the other states in the box. I want it to have some overlap epsilon, where epsilon is as small as possible. So this gives me something, right? I want to minimize the epsilons that I can use a variational principle on. Okay, new page. All right, and then once I have that optimal operator, I will have an optimal correlation function that I create out of these operators. And this, I would like to scale like e to the minus en, where n is the state I'm interested in, times t, plus some extra stuff. So this is the overlap factor for my optimized operator onto all the other states, and then I'll have this tower. Whoops, not that. So again, this is the thing we want to minimize. And this guy I can write in terms of the weights. So remember I had these weights here. Times my original operators. And this I'm going to define in terms of this matrix correlation function. So C is now a matrix with indices ij corresponding to the source index, the source operator j, and the sink operator I. And so I want to minimize, nope. By varying the v's. Okay, so note at this point that this matrix Cij is symmetric because if I swap I and j, I just get back the same thing. And it's also positive because the diagonal entries here, when I equals j, is the product of two, it's the square of an object, right? So the diagonal entries will be positive. The off-diagonal entries are symmetric, and so this matrix is positive definite.